Hi, everybody. New whiteboard marker. Recording. Right, I'll start now. Hi, everyone. Welcome back. Hope everybody enjoyed the school holidays. I know I certainly did, though some of the New South Wales students are still on their school holidays. So today will be less about what's on the slides, and I will do a lot of stuff on the whiteboard. So talking about redox reduction reactions, or the transfer of electrons. The practical applications of this are batteries and fuel cells. So the transfer of electrons produces an electric current. I'm not going to go that deep in because I think it's slightly beyond the scope for those on the Queensland curriculum and anyone else. So I will keep it purely, what's the word? Relatively simple if I can. So sort of chopping and changing all of the resources that I have, putting them together in something logical. So oxidation, reduction, and redox reaction. It all refers to this transfer of electrons. One element is oxidized, one is reduced. And we, as always, we can tell what is the likelihood of this happening based on where it sits in the periodic table. And I will go through that in this. So, identify reduction and oxidation processes. Define a redox reaction in terms of the electron transfer. And all of this is broken up into sections. And then there's a big long equation at the end, which I'll go through on the board. Now, itself will probably take 20 minutes. And determine the oxidation state, or the charge on the individual atom in the molecule. And again, we can determine that based on where it sits in the periodic table. So, I don't know why this has done this again. Chopped off my slides. Slightly too big for Google Slides. So, this is where lots of people get tripped up. Oxidation is the loss of electrons. You might have heard of the term oxidation in when they're talking about rust. So when things start to rust, they begin to lose electrons, they begin to oxidize. So oxidation is loss, reduction is gain. It doesn't make any sense, because how can something be gaining electrons when it's called reduced or reduction, or when it is reduced? And I'm going to go straight to the whiteboard because I mean, it's easier than trying to explain it with words. Electron configurations there. So, oxidation, loss of electrons. So what happens? I'll stop sharing so you can see the whiteboard. What happens is this creates a positive charge. on the atom. So we know electrons are negatively charged. So we take those away, we end up with a positively charged atom. So if we were to look at reduction, so reduction, it gains electrons. And now if we think, okay, electrons are negatively charged, if this element, atom, is gaining electrons, then it's going to become negatively charged. So it will become negatively charged because it's gained electrons which have a negative charge. An easy way, if it's had oxygen added, it's been oxidized. If it's had hydrogen added or oxygen removed, it's called reduction. But I wouldn't worry too much about that. Just remember, oxidation is the loss of electrons. It becomes positively charged or it becomes more positively charged. Reduction, it gains electrons or it becomes negatively charged. I'm just going to leave it behind me because it saves me. So, oil rig, oxidation is loss, reduction is gain. One of the oldest tricks in the book. So, reduction. So this is part of the what's the word? Tutorial questions for you guys. It's to define the following terms. So I'll give you a hint for a couple of them. A redox reaction is a reaction in which there has been a transfer of electrons somewhere. So what I want you guys to, you know what reduction is gaining electrons, oxidation is losing electrons. What is a reducing agent and what is the oxidizing agent? That is your question. So, in order to sort of sum that up a little bit, when something loses electrons, it's oxidized. When something gains electrons, it is said to be reduced. So, we know, let me go back up here. You're wanting to answer those tutorial questions. This will be the answer that you need, preferably in your own words. So, oxidizing agent. So something is oxidized, it loses electrons. Or another way to put that, it gains positive charge. Something is reduced, it gains electrons. Or you could write it gains more negative charge, or it becomes less negative, or it becomes more negative. So the oxidizing agent is the one that becomes more negative because it accepts the electron. It's the one that's stolen the electron. So this is the oxidizing agent. It accepts the electrons. So the compound or the substance that donates the electrons is called a reducing agent. Because this guy, by losing the electrons or giving them away, it causes the other element or compound to become reduced. So the reducing agent is the one that accepts the electrons. And the one that's donated them is the reducing agent. And I'll show you as we go down how we actually figure that out from a chemical reaction. So we look at an equation. So 2 magnesium reacts with O2 to produce 2 magnesium oxide. So if we were to, we need to split it into, remember we have an oxidizing reaction and we have a reducing reaction. So if your brain works in logical steps, this should be enjoyable for you. And then we'll put all of this together at the end. Take 4 or 5 whiteboards to get through to the end. So we'll have 2 mg solid so that just denotes that it's in a solid state and oxygen is in gas, produces so I'm just going to run through what these are. I'm not going to show you how to figure it out yet. We will do that at the end. So in this reaction, we have the reaction between a metal and oxygen. If you see that, then it's almost certainly going to be a reduction reaction. So we have a reduction reaction or half reaction. We have an oxidation. So we have reduction, half reaction, sorry. So O2 in this reaction gains electrons. So O2 is reduced. And I'll show you how to figure this out. I'm just splitting it into this so it's a bit of an overall view. Oxygen is reduced. Mg is oxidized. So the oxidation reaction, and I will show you how to figure this out. I promise. Just bear with me. Just show you what makes it up. So Mg so oxidation, magnesium. Here's a trick. The metal will always be reduced. And depending on where it sits in the periodic table, determines how many electrons it will give away. So metals in group 1 give away 1 electron to become 1 plus. Metals in group 2, Shakara, they give away 2 electrons to become 2 plus. We follow that along. Group 3, give away to be 3 plus. So I know that magnesium is going to be oxidized and oxygen is going to be reduced. So I will leave that there. So oxygen is reduced. Magnesium, being the metal, in group 2 will lose 2 electrons and become 2e minus, whereas oxygen would then become O2 minus. So it's accepted the electrons from magnesium. And another trick for the periodic table, oxygen is in group 6. It accepts 2 electrons to become -2. So look at that, like a match made in it. So when they bond, magnesium will give 2 of its electrons to oxygen when they react. So remember that. There is a slide that goes into that in a bit more detail further on. So, the oxidation numbers. So if we remember back to week 1, the electrons, or the atoms have to have a neutral state. When they react, one can become negatively charged and or they can become positively charged, depending on where they sit on the periodic table. There are exceptions, but generally the metals on the left form positive cations. The elements on the right, the non-metals and the gases, form negative. Now, obviously, there are exceptions to that. So, as they sit, their charge or their oxidation number is 0. So, oxidation number refers to, if it's 0, then it hasn't lost or gained any electron. If it's positive, it means it's given away some of its electrons to something else. If it's negative, it's accepted some electrons. The positives will sit on the left, groups 1, 2, and 3 coming over past the transition metals. Groups 7, 6, and 5 will form negative ions, or they will accept electrons. The metals in group 1, 3 will donate them, and happy days. They will balance out and share them, not quite share them, but they're given away, and it all has to balance out in the end, and that's the final step that will take me maybe 15 minutes to walk through on the board. So, oxidation numbers, uncombined elements, so every element on the periodic table has an oxidation state of 0. Because if it's not reacted or combined with anything, it has to be 0. Now, again, there are exceptions to this rule, but for this purpose of this, has to be 0. Some of these elements will have always have the same oxidation states, or this is a positive or negative charge in certain compounds. So, sum of all of the elements, the sum of the charge. So if we were so the oxidation numbers, plus or minus here, has to equal 0. So these are the rules of oxidation numbers. Has to equal 0. So hydrogen is +1, carbon is neutral, nitrogen is -1. I mean, obviously, it's probably not that, but just for demonstration's sake, has to be 0. Except, except when it's in one of what we call a complex ion. So I have a negative one or positive one, but the sum of, so if it's sulfate SO4 2 minus, this is the charge. Normally it's 0 in all but a couple of these special compounds. But the sum of the oxidation states of this has to equal -2. So, again, we will go into finding some oxidation states soon. So in the compound, the most electronegative, so let's think of the periodic table again. It's in the box. So it's not look like that. The electronegativity values go from left to right. So lowest down here at francium, highest up here at fluorine. So the one that's the furthest to this side is going to be negatively charged. So if you've got H2O, oxygen is over here, hydrogen is here, then oxygen is going to be negatively charged, always. Again, I will go through that I think on the next slide. So, I can use my mouse properly. So, I think I went over this earlier. So the oxidation states of the elements, you can tell based on where they sit on the periodic table. So group 1 metals, +1. They always donate 1 electron when they bond. without exception. Group 2, always donate 2 electrons without fail. Aluminium and other group 3, always +3. Oxygen, always -2. Okay, for the purposes of this, I'm going to say always -2. Unless it's bound to fluorine, then it's +2. Hydrogen, well, we already know that hydrogen is a group 1 metal, so it's always going to be +1. Except with a few noticeable exceptions, but again, I'm going to keep it simple. So chlorine and other elements in group 7, usually for the case of this, -1. So if we put that into practice, we know, again, I'll use my favorite element, sodium chloride. So sodium is in group 1. It will always donate 1 electron. Okay, chlorine is in group 7. It has room and will always accept 1 electron. So +1, Cl will be -1. So we have sodium, which is positively charged, binds with chlorine, which has a 1- charge. Sodium has a 1- charge. The net, so +1 plus -1 equals 0. So the net charge on the molecule is 0. So we can look at that again with water. So water, H2O. This hydrogen is in group 1, and for this case, it's going to be +1. It will always donate 1 electron. It can accept 1 electron in certain situations, but for this, let's just assume it always donates. But there's 2 of them, right? So the charge on hydrogen here is +2. Because it's donated its 2 electrons to hydrogen. Now to oxygen, sorry. With oxygen, you've got, if we look at our rules, it's -2. So +2 plus -2 gives it a net charge of 0. So this oxidation state just tells how many electrons are donated and how many are accepted when 2 things bind together. So do 1 more. I'm going to run out of time. Magnesium oxide, MgO. Magnesium is in group 2. It always forms 2 positive, so it always donates 2 electrons. Oxygen is in group 6. It's 2-. Always accepts 2 electrons. So MgO, the net charge is 0. Happy days. Definitely, probably the most complex topic we've done so far. So, part of the, what can't I say, tutorial question? How to figure out the oxidation states of those elements in those compounds, based on those rules that we just talked about. So I will give you easy one. Copper oxide. So sometimes you can't figure out one of the elements. So copper is a transition metal. I just felt horrible, so I thought I'd put it in there. But we know that oxygen is always, for all intents and purposes, is always 2 minus. So we will always accept 2 electrons. And we know that the rule is that it has to be a charge of 0 on this. So we know that copper will have a positive 2. So I don't think I have any more time to spend on that one. I can do videos of a couple of these as well. So I'm going to use different ones for this, but we can identify the oxidation number from Roman numerals. I'm going to explain using iron and copper, and then if you guys can answer that as another tutorial question. I know I've been slack with giving them out, so I'm going to give out lots of them. So we can tell the oxidation number. So I'm going to go this iron is Fe. Oxide is another way of saying oxygen on the end there. It's always 2 minus. So we know that from this Roman numeral, it's going to be 2 plus. It's donated 2 electrons to oxygen. Oxygen is gone. Yeah, sweet, thanks, mate. Thanks for the electrons. And then they become. So a bit more complicated when we add iron 3. So that says Fe3 plus. Now we know oxygen is always going to be 2 minus, but these have to match, right? So at the moment the charge doesn't match, so they won't bond. So what we need to do, okay, the nearest one that they both go into is 6. So it would be Fe2O3, which will give 2 times 3 is minus 6, plus 3 times 2 equals 6 equals 0. So whatever the Roman numeral here says means the charge on iron, but the charge on oxygen is 2 minus. So you need to balance the charge. So it will be Fe2O3. So you want to answer those questions there as part of the tutorial questions, and I'll do a video on answering that. I'm trying to get through this quickly now because I'm quickly running out of time. I've got my one of the other on board. So redox reactions, and this is where we get into the nitty-gritty. So I am sort of skipping through now. So, any chemical reaction that involves the movement of electrons, or redox, they're called redox reactions. So we have half equations. So the oxidation reaction, which electrons are lost, and the oxidation reaction, which electrons are gained, and then we put them back together. We have balancing equations, so equations have to be balanced on either side. Normally it's just the atoms, but when we're talking about redox reactions, then the charges have to balance on either side. And we use hydrogen and water and electrons to balance, but I will go through that in a minute. So I'm going to use mine on the board because it's quicker. Running out of time. So we need to work out the oxidation states. And this is what I want you guys to try. Once you've watched this, once you've had a read, have a go at this one. I will do a bit more complicated one on the whiteboard. But first you work out the oxidation states. So in order to figure out, and what I did at the beginning, in order to figure out which bit is being reduced and which is being oxidized, you need to know the oxidation state in the beginning, the oxidation state on the other side. Because that will then tell you, okay, what's gained electrons and what's lost electrons. So again, you figure that out, and then you work out the half equation. So which side has been oxidized and which side has been reduced. So again, another tutorial question, and it's all to do with reactivity, and there's a reason we don't put sodium in water, and have a look at that reason. So reactivity refers to the ability or the tendency for an element or an atom to gain or lose electrons. The higher the reactivity, the more likely it is to explode. The most reactive are on the left and the far right, so group 1 and group 7, group 2, and everything else fits in around there. So if you throw pure sodium into water, what is going to happen and why? That'll give you the answer as to why we don't pan for sodium. I mean, you could if you wanted to. So, why do the metals lose their electrons and give them away? And it's because they want to reach this noble gas configuration. And that means that they want to have a full shell of electrons on the outside. They don't want any spaces where electrons can be gained or lost. If you look at group 8, okay, I'm sure I probably said this a number of times, look at group 8, they are perfectly stable. Perfectly stable. All the other elements will gain and lose electrons to try and get to that state. So lithium is the strongest reducing agent. It will very, very quickly lose its one valence electron because it's in group 1. Potassium will do the same thing. Barium, they're all in groups 1, 2, and 3. So calcium, sodium being the 5th most reactive. So the strongest reducing agents. So they are the most likely to give away their electrons. And you can see that, you can tell where they sit based on that charge, group 1 and group 2, down to aluminium, which is in group 3, chromium, group 3. So, if you'd like, sort of a practical application of what we're learning, and that's rust and corrosion. So what is dry corrosion, what is wet corrosion, and wet corrosion, and how do we prevent it? So, and if you're going to write it, do the chemical equations. Don't just tell me why, show me why. This is why things rust. Show me why. I sent all these out, I think, this afternoon. So, why does it keep, I make these in Excel and then, so the rules, those hard and fast rules for those oxidation numbers here in a handy thing, except it's messed up my slide. So you can see them there. I think I just doubled up the slide there. I'm going to do a video for oxidation states because I definitely don't have time to do both of these in the laptop. So I'm going to do for this last, I don't know how long it's going to take, but take a while. I'm going to do a worked exam from beginning to end, using all the steps we did and adding a couple more. And I'll probably, if I ever get the time, do a video for each of the steps. So we're going to, so copper reacts with nitric acid, HNO3, to copper 2 plus NO. I mean, you can already see what's happened here. So copper has lost 2 electrons, but I'm going to do it the whole way. So copper, oxidation state is 0. It's just an element that's been combined. If we were to look at HNO3, oxygen is -6 because it is -2, and there's 3 of them. Nitrogen sits in group 5, so it's +5. Hydrogen, we know from the rules, is +1. So that would equal 0. So something here is going to be reduced. So copper 2 plus, we can see straight away +2. So we know now, no, I'm gonna jump ahead. So not -2 for oxygen, +2 for nitrogen. So we can see that copper has lost 2 of its electrons. We can see here, oxygen is plus, it's still -2 here. I mean, in the compound it's -6. But it's still -2. So nitrogen has gone from an oxidation state of +5 to +2. So nitrogen has been reduced. We know that because its charge has gone from +5 to +2. So it's gained some electrons. Now I know copper has only lost 2 electrons and seemingly nitrogen has gained 3, but we will balance it out at the end. Copper is oxidized. So I'm going to have to go through this relatively quickly because I have 3 hours of meeting after. So we have our half reactions. So we have oxidation. So we know copper was oxidized. So reduction NO. So we need to do a couple of things. These equations aren't balanced. Well, this is 1 copper, 1 copper. But this has an extra hydrogen and 2 extra oxygen. So we take the oxidation reaction, it's balanced in terms of copper. So we simply add two electrons. So now it's balanced because there's 1 copper on each side and the charge balances. So we then have HNO3 . So this one's a bit trickier. Nitrogen is already balanced. We need to balance the oxygen atoms. So the way we do that is we add water. So now the oxygen balances, the nitrogen balances, but the hydrogen doesn't. So we have 1 nitrogen, 3 oxygen, but there's only 1 hydrogen here and 4 over there. So we would simply add 3H+, which balances perfectly. But now we have a positive charge here and we need to balance that. So all we do, add 3 electrons. So now we check oxygen balances, yep. Hydrogen balances, 4, 1, 2, 3, 4. Nitrogen balances, and the charge is still 0 on both sides. So now they're both balanced. Both of our oxidation and our reduction half reactions are balanced. Balanced in terms of the number of each element, the number of atoms, number of moles of atoms. We then have the balance of the charges. So in order to balance, we had to add 3 hydrogen, or 3H+, to balance the hydrogens on both sides. So we needed to add 3 electrons to balance out the charge. So, remember in the beginning I said it looks like there's only been 2 electrons from copper given, but 3 nitrogen lost the oxidation state of 3 oxidation states. So we have to balance the number of electrons going across from one side to the other. So our oxidation reaction only has 2 electrons being transferred, whereas our reduction has 3. So that's not right. We can't continue on with that. So the lowest common denominator between 2 and 3 is 6. So we would then, this is where it can get a little bit tricky and confusing. So So we would then have, so it's copper. And we need to make this 6 electrons being transferred. So what we do here, so we just change that to 3 copper transferring, which loses 2 electrons per copper. So we then have to add 6 electrons to this side. Oh, okay, now. So this is our oxidation. The reduction is a bit trickier. So we have 2. Because remember, there's 3 electrons, so we have to times it by 2, times everything by 2. We have 3 H plus, so again, everything gets times by 2. So everything gets times by 2. That means there's 6 electrons being transferred in both of these. It balances. If both sides have 6 electrons, so this would be 6, we can just cancel those out. So what it would be, so we would then need to combine all of this together. So both of these have 6 electrons. We cancel those out. So the final answer of balancing everything, and we need to then recombine the oxidation and the reduction reactions. So our oxidation reaction is 3 copper, not 3 copper. The reduction reaction is 2 HNO3. Sorry. So what we need to do is combine these together. So what we do is we've got 6 electrons on both sides, so they cancel out. We don't need them. So if there's 6 electrons here, 6 electrons here, they don't need to appear. So we need to combine these back into one normal equation. So the answer would be, and I'll explain it in 5 minutes. We combine these together. After we've deleted the electrons, that is the final redox reaction. So 3 molecules of copper react with 2 molecules of nitric acid, 6 electrons are transferred between here and here. So 6 electrons are lost here. And if we look at, so technically they go to nitrogen. So nitrogen goes from +5 to +2. And that is the final equation. I'm going to put up some videos breaking this down into smaller chunks because it's a lot to go through. It even after all these years hurts my brain.